Right, in this video we're looking at 2016 Year 10 end of year exam, and we have a series of questions which teachers will be explaining why they gave the marks, where they did. So here we go, enjoy.
Right, nice and easy question. Most people score very well on this question. So the very first one is just pure recall. Can you tell me what the equation is? And the equation is F equals A, or force equals mass times acceleration. Surprisingly large number, although a minority, actually got that wrong, which had consequences for later in the question, when you then needed to use this equation to calculate the force needed to produce this acceleration. So the acceleration is 1.5, the mass, so A is 1.5 meters per second squared, M is 38 kilograms. So you're starting with F equals ma. It's asking you to find F, so we don't even need to do any rearrangement. It's just 38 times by 1.5, which equals, so 57 newtons. Okay, the final part. Suggest a reason why the force exerted and assessed by the man must be greater than the force calculated. Okay, now there are a number of reasons for this. Okay, the simplest of which is that there will be friction between the sled and the ground. Yeah, so that's your number one reason. A slightly less obvious reason is that because the man is pulling at an angle here, so you can see the rope, or the force from the rope, will actually be at an upwards angle, so he's actually slightly lifting the sled as well as pulling it along, so the force is essentially divided between those two parts. So something along the lines of he's pulling at an angle, so not all the force is accelerating the sled horizontally. That's it.
Okay, here's our question, looking at a velocity time graph, bearing in mind, of course, that the gradient will be the acceleration and the area underneath the distance. Those are two things that you should be quickly pick up on. And it says here, we're looking for a bus travels, the graph shows, state the velocity of 25 seconds, 20, 30, 25, followed up. You've got to be careful there. It's along the top, so I would say that is 0.3, 1, 2, 3. So each one's 0.2, that's going to be 7 point, that's going to be, oh wait, sorry, I've measured that incorrectly, sorry. 25 is actually along there, 1, 2, 3, 4, 5, 25 up perfectly at 6 meters per second. So let's try and write that along, 25. See how easy it is to get it wrong. And that comes across to 6. So therefore, state the velocity. We have 6. Easy one marker. How long is the bus stationary during its journey? Now, careful here. This is the only point in which it's stationary. This is a constant speed, or velocity. This is the stationary bit. So therefore I think that the difference there is 10 seconds. Good. State the equation that links acceleration, change in velocity time. Always write it as a word equation, might be easier. So state the equation, acceleration, velocity. So we can either say acceleration is the change in velocity over the change in time, or acceleration is the change in velocity divided by the time taken. Good. Either of those is perfectly right. Calculate the acceleration of the bus in the first 10 seconds. So let's just go back to here. We're looking for the first 10 seconds. Of course, that suggests that we should be looking for a gradient, the gradient of that line. So how do you work out the gradient? Well, you want the rise over the run. And of course, we know that the run is 10 seconds, and the rise is 12 meters per second. So therefore, going back down here, so that's 10 over 12 over 2, we have the gradient is the rise over the run, which is 12 meters per second over 10 seconds, giving us 1.2 meters per second squared. Good. Remember, probably here we're looking for a mark of that assumption correct. And there's 3 of them to incorporate. The correct answer and the unit. The unit is very important though. Good. Okay then. So let's take a look at the next part. The next part's asking for state the equation linking average speed, distance, and time. So I imagine most would probably write something like speed is distance over time. However, what we're really looking for is, so strike that one out, what we're really looking for is average speed is total distance divided by the time taken. Good. So therefore let's look at the numbers. The bus moves a total distance of, so we have a distance, calculate the speed. The bus moves a total distance of 390, so therefore, if you can see in the previous question, I won't jump back, but we know that the average speed, let's call it v, is going to be the total distance divided by time. Note that that is distance that we're talking about. And the distance is 390, and I will divide that by the 60 seconds that it takes. 60 seconds, so that's meters divided by seconds, gives us an average speed of 6.5 meters per second. Where do the marks come from? Marks come from, of the 3, they're coming from 1, 2, 3. Because the units needed, answers needed, and then in actual fact, probably, it's more likely to be substitution will be, because that you've stated already above. Wonderful. So the bus travels a further 30 seconds. Sorry, the bus travels further in the first 30 seconds of journey than it does in the last 30. Explain how this is from the graph. Well, I'm not going to jump back. However, this is going to reference, of course, it's talking about travels further. So this is relating to a distance. And distance is going to be the same as area under the graph. So with that knowledge to mind, what you're going to do is you're going to measure the area in 30 seconds and the area in the last 30, and then you're going to notice that that is greater than the other one. So this is greater than that one, hence it's travelled further. Good. As opposed to travelling least far, so that's where you get the marks from. An assumption of, and then comparing the areas between the two. Wonderful. Okay, here's our question on a skydiver jumping from an aircraft, mass of 70 kilograms. What's the equation relating mass, weight, and thing? Well, we just need to learn this one. weight is equal to mg. I think the equation is fine for that. Learn it. Calculate the weight of the skydiver. 3 marks, so we're going to be looking for, and we won't be penalised again for that one, but we're going to definitely look for the substitution multiplied by 10 on Earth, g on Earth, and that's going to give us 700, and then we're going to need to know the newtons, so 700, and the answer's in newtons. So a tick for knowing that, a tick for getting that, and a tick for getting that correct. Oops. Good. The graph now shows the vertical velocity over the first 40 seconds. The parachute is not open during this time, so this is free fall, reaching a terminal velocity. Okay, so let's take a look at what it's asking of us. It's saying, explain the shape of the graph in terms of forces. Ooh, tricky. Right, let me just remind myself of velocity time, and it was doing that. So, what we want to do is try and break this down into 4 parts and explain what's going on. We want to state that we have a downward force, which is known as weight, and initially that is all that's acting on this body. So therefore we get an acceleration. Bearing in mind, if there is a resultant force, it's the same as saying there's an acceleration or a change in speed. So when they initially jump out, let's call it part 1, let's go 2, let's go 3. At part 1, we have a resultant force, the weight, that's all that's acting at that point, and therefore we have an acceleration, so it's very steep on that part. Okay, but next point, let's do number 2, as skydiver accelerates, so their speed increases. Good. Increased speed equals greater resistance, air resistance. Wonderful. Therefore, the new resultant force is going to be the weight minus the drag. And that is going to be less than the weight. So this here, the weight minus the drag, will be less than weight. So whatever your initial velocity acceleration was here, which is due to the weight, now it's been reduced, so therefore acceleration reduces. So the acceleration reduces. And more crucially, at point 3, you'll get to a point where the weight is equal to the drag. Therefore, the resultant force is 0. So the acceleration is 0. So you reach a constant velocity, i.e. a terminal velocity. Try and draw what's happening here. You have a, well, it's upside down. I won't draw what's happening there. I hope that makes sense. Good. Next one. Draw the labeled directions at a constant velocity. You're looking for the 2 labeled arrows represent the forces on. And remember, with these, you should always write down the name of them. So let's do drag and weight. This should always go from the centre of mass. This should always be represented by whatever, but they need to be the same length. And yeah, so the same length and correctly labelled. and the correct direction, of course, but that goes without saying. I hope you understand what's going on. And the reason why it's because the same length, because the resultant force must equal 0. Good, I hope that makes sense. Right, back to the skydiver opens the parachute. Continue the line on the graph to show what's happening. So, what's going to take place here is at that speed there, when this person opens the parachute, you're going to have a huge drag compared to the weight. So therefore you're going to get a huge resultant force, hence acceleration, which is actually a de-acceleration. So this is going to steeply go down. But then, of course, as it gets slower, so it will reach eventually a point where the drag equals the weight, and that's our second terminal velocity. Perfect. For the 2 marks, I just think you just need it to swing down. Oh, let me do that with another pen type. You need to just swing down violently and then level off for your 2 marks. Excellent. Let's see what next we've got. Okay. Electrical circuits. To define the term current electrical circuits, you should just memorize it. I don't think there should be a massive problem with this one. And when you memorize it, you need to know it's the rate of flow of charge or even better, it's the number of coulombs per second. What's the equation that links? Well, this is simple. Q is equal to I times T, or charge is equal to current times time. Good. Damien has a small electric motor in which has 60 coulombs. Passes through in 2 minutes. Calculate the value of 3 marks. Good. So let's go for this then. So I want to calculate the current. So I is equal to Q over T, because if Q equals I times T, then all I've done is I've dragged that to the underside. Good. I want 60 in here and then 2 minutes, but note it's in minutes and I want it into seconds, so times that by 60, leaving me with 0.5 coulombs. Please note it's in coulombs, so you've already had that mark for the previously, so therefore a mark for substitution. Sorry, a mark for understanding that it's in minutes to seconds, a mark for the answer and a mark for the unit. Okay, the energy supplied to the motor this time. Energy supplied to the motor if it runs continuously for 1 hour. Okay, again, just quickly, we know 1 hour equals 60 minutes and 60 seconds, which is 3600 seconds. And I now know that it's asking for the energy supplied. And I know my current is 0.5. Do you know what? Sorry, I'm just going to go back here a bit. That's not right there. That's 0.5 amps. Silly mistake on my behalf, because we're looking for the current, hence it should be in amps. Okay, so yeah, there's something wrong with that figure. So therefore, how do we work out the energy supplied if we've got the time, and what else do we need? So simply, energy equals the charge times the voltage. And the charge is the current times time times the voltage. So if we know the current from the previous side is 0.5, times that by 3600, and times it by 5, gives us 2.5 by 3600. And I might need to just make absolutely sure I know the answer to this one. It's going to be 9,000 joules. Good. So a mark for knowing this equation, a mark for conversion, a mark for the answer, a mark for the unit, and a mark for the workings. 5 of them. Wonderful. Let's see if there's anything more to this question, or even to the next one. Nope, we're on to the next one, but it says, you must use a pencil and ruler to draw the diagram. In this question, complete the circuit by adding a resistor and ammeter with series with. Right, series means that we're going to be just joining it up in one big loop, but we want to add an ammeter with the bulb. So I like to draw my ammeters on the right hand side, I don't know why, just a little quirk, and a resistor, both in series. We've done it there. Perfect. Simon wants to find out the resistance. The resistor add additional components that he will need. Well, I hope you remember this from the work, but in order to work out the resistance, you need the voltage and the current. So, tick, we've got the current, but what about the voltage? You need a voltmeter, and the important idea is that this should be in parallel around the component. So, 2 bits in parallel around the components. Okay, so what additional piece does he need? He needs a voltmeter. And we've added it in the circuit. State the measurements Simon needs to take and explain how to use them to create a value for the resistance. Well, as I said before, here you need to measure the voltage and the current and then divide it. I think those are where your 3 marks are going. So let's state that you need to measure the voltage. You need to measure the current. Then you need to use the equation R equals V over I. Measure, measure, calculate. Straightforward. Now we have a look at a voltage current graph, and instantly you should look at this and go, oh, I know what this is. This is just like a diode. That's the shape of a diode. It says Simon decides to play with light emitting diode. Good, it looks like that. He plans to set up the circuit as shown in figure A. Wonderful. His friend Andy shows him the graph. B, and shows how the current through varies. Wonderful. All recall. Simon thinks the LED will light up in the circuit when he connects it. Andy disagrees, think it will remain turned off. Who do I think is right? Probably suggests what do I think might Andy be thinking? And what do I think? Well, 2 points first. One is diodes like the current to go through them in the right direction. That's the way the current is going to be drawn, driven, so that's not a problem, so we need to ignore that. However, I do think Andy is probably right, and I will go with Andy because, and this is quite a tricky question, but what we need to appreciate is the respective sizes of these 2 resistors. If I work them out as a ratio with regards to one another, note this is in kilo ohms, so therefore I've got 1 to 50,000 ohms. 1 to 50,000. That means that I will have, for every 1 bit of voltage I have here, I will have 50,000 across there. So, and if the total is only 1.5, then pretty much all of the voltage will be dropped over this one, and no voltage will be dropped over that one. Therefore, if there's no voltage, very small potential difference, you're not going to have a current flowing. It's not going to light up. So with that in mind, we will say that the voltage across LED is very small. And you need 0.5 volts, see above here, in order for it to light up. Good. And if you wanted to do a calculation, you could say that 10 to 500 times 10 to the 3 is the same as 1 to 50,000. And so therefore 1.5 divided by the total, which is 50,000 plus 1, multiplied by 1 will give you the voltage across the LED, because it's a ratio. So I'm taking total resistance multiplied by the resistance I'm after. And that gives me a VV small voltage. Hence it won't light up. Wonderful. Next question. Alistair and I have been testing 2 pieces of wire. The results are shown. Another current voltage. These are steep. These have gradients. And remember to ourselves that the gradient is equal to 1 over the resistance. I'm sure that's what it's going to allude to in the first question. And the reason why that is because the gradient is the rise over the run, which is the same as the current divided by the voltage, which is 1 over R. So just bear that in mind. Whoops, let's do it in blue. Okay, great. So, how does a resistance A change as the voltage increases? Well, the resistance stays the same. I'll explain why. Because the gradient is the same. The gradient is the same up here as it is down there, so therefore that means the resistance stays the same. Good. Similarly, how can you tell that the resistors are different? Well, because they've got different gradients. Okay. Which resistor has the higher rating? Well, remember I said it's proportional to a 1 over, so the shallowest gradient will have the highest resistance. Hence, we have resistor B. And if they're made of the same material, give one reason for the difference in resistance. Well, this could be a number of things, physical things. It could be the length is different. It could be the area is different, even the temperature. But we're only looking for one of those marks of many possibilities. Okay, here we have 3 circuits with 2 diodes. And which ones would they be on? Do you remember we talked about this, that implies it's only going to let current flow in that direction. Current always moves from the larger to the smaller, therefore this is going around, that's going around successfully. This one is blocked, this one is successful, but it's blocked. So therefore it can't be this one, it can't be that one, so therefore it's J. Wonderful.
Okay, so we're looking at question 7 here. This question is to do with a Geiger-Müller tube which is being used to measure the background radiation in a laboratory. It says that the we're resetting the counter to 0, waiting 1 minute, and then looking at what count has been recorded, and we're going to repeat that process a couple of times. Now we have these readings, 11, 16, 12, and the question asks why the readings are different. It suggests, one, the teacher did not reset the counter to 0. Now this would introduce a systematic error. However, that systematic error only shifts the results up or down. It doesn't account for why we would be getting 3 different readings for what we think should be the same result. The temperature of the laboratory is a red herring. The temperature has nothing to do with radioactive decay, or at least not in these terms, because it's been a spontaneous decay. The answer is B. It's a random process, radioactivity. So we could take this reading over and over and over, and we would expect, because it's of the random nature, to get different readings each time. However, they would average to some predictable value. Now, part B just asks us to work out what that average is. So we need to average these readings, 11, 16, and 12. It's fairly straightforward. Just 11 plus 16 plus 12, and divide by the number of things that we've taken. So the average equals this, which gives us 13 counts. And that should really be per minute. So we've now introduced a radioactive source, and we're measuring the activity of that source. And it asks us to work out how many counts were due to the radiation from the radioactive source. Well, we know that the count in the 1 minute was 118, but we also, so that's 118 counts per minute, but we also know that there was an average background count of 13 counts per minute. So we subtract one from the other, and we end up with a count rate of 105, and this should be counts per minute. Now, the marks were taken off if you didn't put any units there, we gave you the benefit of the doubt, but if you put the wrong units, that does actually make the answer wrong. So counts per second or becquerels there is actually gives you the wrong answer. Now that brings us on to the last part of the question, which is what is the standard unit for the activity of a source? Now, counts per minute isn't the standard unit. The standard unit is actually the becquerel, so which we shorten it to this, but the long one is spelt like this. It's quite a tricky spelling. That is equal to a count per second, but we were looking for that word becquerel to get the marks.
Right, now this question is talking about radioactivity, radioactive sources, and it's looking to the poor lizard in the biology department. It's got a tumour and you want to kill that tumour off. So you need ionising radiation, which you have here, in order to kill it. But lizard, of course, you don't want to kill the lizard, you just want to kill the tumour, whilst not killing anything else in the process. So, what properties do we have? And what's the best source in order for this, and why? 4 marks. Okay, so we want type first. That's important. Then we want to know why. Is that one important? Then we want to know about the half-life and why that's important. So let's talk about each of those. What type? First of all, alpha. And why? Because we want it to be damaging, but not penetrating. In other words, I don't want it to get out of the lizard. Beta will get out of the lizard. Gamma gets out of the lizard. I want alpha that stays inside the lizard first and foremost, but also alpha is the most ionising, so we'll have most ionising. Perfect. Okay, what's my next point? Half-life. I want it to be short. I want it to be long enough to do damage to this tumour, but I don't want it to last so long that it just stays in the body and does damage to the body after the tumour's gone. So of these two that I've got, I'm slowly eradicating some of them. The beta I don't want, the gamma I don't want. I don't want a long half-life, so therefore this is what I've got. Wonderful, but as I've said, there's 4 marks here, so what else can we talk about? We need to give a reason of why that is, because we don't want it in the body too long. Okay, good. Lead contains 82 protons. How many neutrons does it contain? Well, we should simply know that this number here is equal to an addition of the number of protons plus the number of neutrons. So therefore the number of neutrons must be the difference, which gives us 1, 2, 8 as a number. Tick. Okay, next bit, we need to complete the equation. You should know that all these numbers along the top add up and all these numbers along the bottom add up. What's the information that you're not given? You're not given beta, so you need to assume and understand what beta is. If this is beta, we know that's 0 minus 1 because it's a fast moving electron. Minus 1 sorry, wrong way up, hold on. We want beta, we want minus 1, 0. Because it's an electron, so it has a minus 1 charge, but it doesn't really have a mass to it. So if everything along the top must have to add up, that must be 210, because equal sign. And because this is minus 1, what plus to that must be 83, plus minus 1 gives us 82. Excellent, 3 marks. 1 mark for those two. 1 mark for beta and 1 for those two. Right, finally, what is a beta particle composed of? Well, this is tricky. It comes from the nucleus, but it is actually an electron. But not just any electron, it's a fast-moving electron. Good.
Hi there. Right, I'm going to talk about question 9 on the Year 10 exam, which is this one here, and it's talking about nuclear fission. You're given, as you can see, an equation which has got actually 2 right arrows. So this is the first part of the process. So a neutron plus is absorbed actually by a uranium-235 and produces uranium-236. This is describing the fission process here, whereby uranium splits into barium 141 and krypton 92, with 3 additional neutrons and some energy. So in the first question, you are asked to use the information in the equation to describe the process of nuclear fission. And then, this is key, be as specific as you can. So it's asking you both generically what is fission and, in this situation, what is actually occurring. So, there are 4 marks to this question. It could easily have been a 6 marker, but I'm going to go through the 4 marks that I offered. So, the main points then. So a slow-moving neutron for 1 mark is absorbed by a uranium, and I didn't mind whether or not you use the symbol or the word, 235 nucleus. Now this is really important. Atoms have nothing to do with this. we're not interested in electrons, we are only interested in the nucleus. So if you mentioned atom, it would have been ignored. Okay? A slow-moving neutron is absorbed by uranium-235 nucleus to become uranium-236. So if you mentioned the uranium absorbing the neutron, you get the second mark. Note that you should not say it reacts with, nor that it is added to. You're interested in the fact that the neutron is absorbed by a uranium-235 nucleus. Now, the next stage is that uranium-236 is unstable and therefore splits into two, in this case, two smaller nuclei, which is barium and chromium. In addition to three fast-moving neutrons. If you just said three neutrons, that would have been okay, just about, and energy. Right, so let's see where the other marks came from. So you've got slow-moving neutron absorbed by uranium nucleus to become uranium-236, which is unstable. That's my third mark. And then splits into two smaller nuclei. So you would have got the fourth mark for either saying two smaller nuclei. You could have said barium and chromium. And you could have had another mark here for the three neutrons and the energy. If you mention things about if you mention things like the fact that the numbers up here, if you look back up to the equation, 431, 141 plus 92 plus 1 will equal 236. And again, 92 is equal to 56 plus 36 plus 0 plus, well, obviously there's no numbers here. But the numbers on the top add up to the 236, and the numbers on the bottom add up to 92. So that would have gotten you credit there. Okay. Problems came in where people mentioned atom rather than nucleus, where people were talking about reacting rather than being absorbed, and on the whole it was well done. Okay, now moving on to the next question. Barium-141 has a half-life of 18 minutes. Define what is meant by half-life. Most people got 1 out of 2 for this. I got 1 mark for saying the time taken. And then there are 3 options. So half-life is either the time taken for the count rate of the parent sample of isotopes to halve, it's a verb, or you could have said the time taken for the mass of the parent isotope sample to halve, or it could have been for the number of parent nuclei to halve. Okay? So in this question here, we have got a sample of nuclear waste from the reactor contains 32 grams of barium 141. And the question is, how much time will pass until there is only 2 grams of the isotope remaining in the sample? Well, what we need to remember from the previous question is that the half-life, we've just had to define half-life, the half-life of barium 141 is 18 minutes. Right, so we have to first establish how many half-lives have passed, and then after the half-life is, after we've worked that out, you need to turn that into time. Okay, so the easiest way of doing this is saying, well, we start with 32 grams. After one half-life, we will have 16 grams. Note the arrows represent the half-lives here. After a second half-life, it will have halved again to 8 grams. After a third half-life, it will have halved again to 4 grams, and then after a fourth half-life, it will be 2 grams. So the number of half-lives is 1, 2, 3, 4. So we've got 4 half-lives. We need to turn this into a time now. Quite a lot of people just left it at 4. So the time passed must be equal to 4 half-lives multiplied by the 18 minutes per half-life, and that will give you 72 minutes. Don't forget the unit. So 1 for identifying that there are 4 half-lives in the first place, 1 for multiplying it by 18, and then 1 for identifying 72 and getting the unit as well, minutes. If you left the minutes off, you didn't get that final mark. There is one other way in which you can do this. Some people decided that to use it numerically, so they knew that if you divided 32 by 2 to the power of the number of half-lives, I'm going to call it n here, must be equal to what we have left, 2 grams. So the easiest way to do this would be to multiply both up by 2n. So you get 32 equals 2 times 2n. And then dividing both sides by 2. You could also make it 2 to the n plus 1, but that's confusing. So 32 divided by 2 is 16, is equal to 2 to the n. And so you have to think, to get 16, what do you have to raise 2 to the power of? So 2 to the power of 2 is 4, 2 to the power of 3 is 8, and 2 to the power of 4 is 16. So n, which is the number of half-lives, is equal to 4. And then you can go straight back to this point here and do this bit again. Okay? Great. Now moving swiftly onwards, the final part of the question was the part that people found the most difficult. I think really what's happened here is that people have not necessarily learned off by heart the definition of control rods and moderators. But also I'd like to point out that there are some difficult parts of the question. So control rods and moderators are crucial parts of the nuclear reactor. Describe what they do and the effect they have on the process of generating energy in the power station. Okay, so the key point about the control rods is that they are there in order to reduce the power output. Okay, reduce the power or energy output in the power station. By absorbing neutrons. So they literally take neutrons. So when the fission occurs, and you have uranium-236 goes to barium or krypton, and then these three other neutrons, it may absorb one or more or all of these neutrons, and they can therefore not go on to be absorbed by further uranium nuclei. So if you said something like, if you mentioned absorbing a neutron, then you got a mark. If you mentioned something about, when they absorb the neutrons, they reduce the energy generated, or something similar, like if people mentioned fewer fission reactions can occur, because of course each fission reaction gives rise to energy. So if you mentioned that fewer fission reactions can occur, then I accepted that mark. The moderator, this one was much more difficult for people. I think you've either learned it or you haven't. Now the function of the moderator is actually to slow down those fast fission neutrons, those fast neutrons from fission. If you noticed on the previous page, I said that we slowed down fast neutrons. We said that a slow neutron was absorbed by uranium-235. So you have a neutron that is absorbed by a uranium-235, and it produces uranium-236. Now this neutron has to be slow, otherwise it is unlikely to be absorbed. It'll probably just go straight through it. Okay? But the neutrons that come out from these are fast. These neutrons are fast fission neutrons. So somehow they have to be slowed down. To slow something down, you bang into it in the opposite direction. So here you can have a neutron that's going really fast in that direction. And here you might have a particle in the moderator. Might be water. Might be a hydrogen atom or something like that. That when the neutron hits into it, the neutron slows down, and as a result, and the hydrogen is sped up. Hydrogen, I'll put an H plus this, for example. Okay? So the point is that this has gone from fast to slow. Now, what's the net effect of this? So we've discussed what they do. They slow down the fast neutrons from fission so that they can be absorbed by uranium-235. This allows more fission reaction, fission processes to take place. And so the energy generated will increase. Now, I was quite lenient, I have to say, on the marking of this, but I think it's worth learning for next year. So here, if you mentioned slowing down neutrons, you didn't have to say fast. slowing down neutrons from fission. And then the second mark could either be for being absorbed by 235. I just wanted to see that there was what they did and why, or if you mentioned that in order to get more energy generated, I allowed that as well. Fantastic.
Right, we're talking now about Brownian motion, Robert Brown, 1827. And for whatever reason, he was trying to investigate something, but he discovered what he described Brownian motion. And what did he observe? He observed constantly changing direction of pollen. Or indeed, you could say moving around randomly. Good. What caused that to happen? Well, if you have your pollen and you have your invisible particles, they bump into it, thereby causing this thing to move around and to jitter. This bit is invisible. So therefore, pollen was being bombarded by water particles. Molecules, should I say. Molecules is probably better. Okay, what else? And that created the the movement in the pollen. Good. I think that's it. Short and sweet.
Calculate the volume of the pebble in meters cubed, not centimeters cubed. Now it's 260 minus 200. That will give you 60 centimeters cube. And 60 centimeters cube is 60 divided by 1 million meters cube. And that equals 6 times 10 to the power minus 5 meters cube, or if you wish, 0.00006 meters cube. Density equals mass over volume. In the case of the grams, it's 72 over 60, which is 1.2 grams per centimetre cube. That will be 1,000 times greater.
Splendid. So now we're on to question 12. In question 12, we're talking about Simon being a pirate in the 17th century, wanting to dive for sunken treasure, and introducing the idea of a diving bell. It's a low-tech device which simply traps a large pocket of air, so there'll be an air bubble in this region here, so that the driver can return to it at intervals in order to breathe. The pressure of the air in the bell is the same as the pressure outside at any particular depth. So the pressure at this point, you could say, is the depth outside. And okay, you could say, well, it's got a different depth, and you could argue there'd be a different pressure in there. However, in the question, you don't need to worry about that. So let's have a look at what the question is asking. So first of all, state the equation. It's a simple equation. So if you've learned it, you'd be fine. So the pressure difference is equal to depth, so height, h rho g, depth times gravitational field strength, and I really didn't mind if you used symbols. Depth times gravitational field strength, h rho times density of the seawater. Okay, if you put pressure difference, or even without the triangle, equals h rho g, then that would have been absolutely fine. So the idea of that is to get you thinking about the next question. Simon lowers his diving bell to a depth of 30 metres. The density of the seawater is here. At this stage you could think, oh, I should have known the density previously. Calculate the pressure difference due to the seawater at that depth. So you've got the depth and you've got the density. Give your answer in kilopascals. Now make sure you read the question because quite a few people forgot to convert into kilopascals. So let's have a look then. So pressure is equal to H rho G, pressure difference, which is equal to, I'm going to put that there, 30 times, in metres, remember, has to be in metres because you've got a metre here in the density. So that's consistent, lovely. And then on the front of the paper it says use G is equal to 10, so G is equal to 10 newtons per kilogram, and if you calculate that, then you find that you get 309,000 pascals, which of course is 309 kilopascals, because 1,000 pascals is a kilopascal, of course. So that's 309,000 pascals. So 309 kilopascals. Splendid. Great. On question C, we're going to calculate the total pressure at 30 metres given the atmospheric pressure. The pressure at the surface is 101 kilopascals. Well, remember in the previous question we calculated the pressure at a depth, the pressure due to the water. So the change in pressure due to the water was equal to 309 kilopascals. So the total pressure is simply that in addition, so that's due to the water, plus due to the air. So the total is 410 kilopascals. Make sure you add up correctly there. It's very easy to make minor slip-ups at this stage. The original volume of water in the air pocket is 8.2 metres cubed, but when taken down to a depth of 30 metres, its volume decreases as the pressure increases. Now this is a tricky question. You have to remember the formula and you have to apply it. So first of all, let's underline the important words. So you've got a depth of 30 metres, you've got volume, you've got pressure, you're calculating the new volume, and you've got the original volume. So that's going to be V1. The new volume is going to be V2. Okay. Now remember, at the surface, the pressure is just atmospheric pressure, so 101 kilopascals, okay? And V1 is 8.2 metres cubed. And we know at 30 metres, your final pressure is what you calculated in the previous question. Remember, it gave you a clue. You'll need to use your answer to part C. This is part C. This is your answer. So that'll be 410 kilopascals there. And V2 is what we're trying to find. So that should ring some bells. We're trying to think out what your equation is going to be. It's a matter of getting it right, of course. So P1V1 equals P2V2. How can you remind yourself which way it goes? Well, the fact that you were told the volume decreases and the pressure increases means that you can check that you've got the right one. Okay? So P1V1 must be a constant, so if P goes down, then V must go up, and vice versa. So let's just plug the numbers in. What are we trying to find? V2. Let's get V2 on its own. So to do that, we need to divide both sides by P2. So that becomes P1V1 divided by P2 is equal to V2. So that's what we want to find. So let's plug the numbers in now. And it's so easy once you've laid it out. So P1 is 101 kilopascals. They're all in the same unit. So that's going to divide out. So we're just going to put 101 there. The volume is 8.2 meters cubed. P2 on the bottom is this here. So let's put that in. 410. Notice that I would have had kilopascals at the top, kilopascals at the bottom, so I'm not putting the kilo in, okay? And then if you do the sum, then that comes out at around 2.02. Now remember, this is in meters cubed, so your answer has to be in meters cubed. The big assumption that we made in this question was that, well, we know that no air escaped. That's fine, because changing the amount of air will change the pressure you feel for a given volume. And quite a few people said, oh, that the diver might have breathed some of the air. Well, true, I can understand that, but we're assuming that there is the same amount of air in there as previously. So the main assumption is that the temperature is constant. Remember, you might remember if you're doing, you should remember that P1 over T1 is also equal to P2 over T2. So if you change the temperature, you can change the pressure, and that's not what we want to do. We want the only reason that the pressure changes to be that the volume has changed. So temperature has to be constant. There you go, well done. It is worth perhaps adding in the marks here, so let's just show that here it was the straightforward equation working ANSI unit. So equation 1, working 1. Actually, it was equation, rearrangement, and there we go. Something like that. If you got it all right, you'd have got 4 marks, okay? And temperature is constant, that's a single answer. And again, you had to get the whole thing right up at the top. Thanks very much.